Okay, we're live. So this was 5 days out from the exam and we're looking at similarity. And I don't know about you, but it's pretty exciting at the moment. We've got the northern and southern lights going crazy, and that's the reason for my delay today. But I hope you got a chance to see it. Absolutely magical, once in a lifetime, and a great break from all this work. Okay, so similarity with triangles, areas and volumes today. Quite a short one. If anyone turns up, I will be surprised. But if you do, please ask your questions. And a quick reminder that if you want these questions before the live stream, then please do go to Patreon. My Patreon is here on the right, patreon.com/tformula, where you'll get these questions ahead of time, which is so much better. You're just going to watch me, you're not going to learn as much, so you have to walk that path yourself. We 5 days out from the exam, meaning next live session won't happen until after the first one. Doesn't mean to say that it won't be useful, because you've still got another couple of weeks, so we'll be going for another few weeks and still got your chance to ask questions, and I'm sure there'll be plenty after that first exam. And when all the questions get released on some student website, there's a couple of them that do tend to release, and some students even remember their questions off by heart and repost, so there's no stopping that, and there'll be plenty of conversations. Okay, let's get started. I know it's about 2 p.m, just after 2 p.m. in England, so good stuff. Nice time of the day. It's pretty late here, so let's get going. Elizabeth is about 1.4 meters tall and is standing in a large park with family. So I haven't actually done these questions, so I designed them and I think they'll work, but this is reminding me that I haven't actually had a look at these ones beforehand. It's been a busy week, so this will be fun. Elizabeth is about 1.4 meters tall and is standing in a large park with family. So this is the fun of maths, I suppose. You can model people in strange ways. So essentially that's Elizabeth, 1.4 meters. We don't really need to put Elizabeth E, but whatever. And she's standing 30 meters from a bandstand. In fact, let's try and make this a really straight line. Hey, that's not bad, eh? And let's say there's the bandstand there, like that. And her dad is 2 meters nearer to the bandstand. So if that's 1.4, maybe something like this. And it says that they appear to be as tall as the structure. So if we drew a straight line from the eyesight, let's say this is the eyesight of, are our eyes typically at the top of our head? Probably not. Like I know we've got some like freedom here to interpret the question. If it says Elizabeth's eyes are 1.4 meters off the ground, that's something different. I'm going to say that if we take off 10 centimeters, this is going to be more like 1.3 meters. So let's say that goes to there. But this would be more like 1.3 meters, what we're trying to get at here, because that's what her viewing angle is. And then the dad is here. Now, if he appears to be as tall as this thing, that means he'll be in line with it. So my figure, and dad is 2 meters taller and is 1.8 meters. So this here be 1.8 meters. And then this whole length away is 30. I guess we can put that in like that. All right, so without thinking, oh, I know where this is going, I just have put visualizing this question to paper. So, the thing is everything. How tall is the bandstand? So something we want to know, so we'll give it a letter. Yeah, and we've got some work to do. Well, I suppose there's a few angles here we go at, but essentially this would reach the bottom at some point and be some sort of triangle. I don't know if that's going to be useful, but I'm going to go with, I'm going to get rid of that so it's a bit more clear. Essentially what we have here is a similar shape. And we can draw these separately. And it's hard to see when it's inside, right? This, the reason we know it's similar, and in fact it's easier because it's easier to see with triangles because you've seen similar triangles before. But once you've got a triangle that's inside a triangle, you see, like I just draw a straight line there, you know that these angles are all the same. They share the bottom angle and they share this angle. And they've both got right angles. So you can see that they're going to be similar shapes because one is just bigger than the other. But they've got the same angles and stuff, right? So if it helps you to imagine a triangle, then fine. But the fact that it's inside the other one makes it hard to see. So we draw it out separately. There's a very strange shape that we have here, but we'll do it anyway. Nice trapezium. And then we've got a trapezium on the inside, right? So we can draw that separately. Something like that, right? So, no, I'm going to elongate. Yeah, that's about right. Okay, so these are the two shapes. So if we call that A and we call that B, A is the overall big one. Right, and that has 30 on the bottom. It's the full length. Where are we at? Yeah, and then the side here is 1.3. And then the side here is 1.8. But this also contains this x here. So there's a couple of things I guess we could do with this. I mean, we're going to first of all find the link between the two. So we find the two sides that are linked, and it's those two. We have information on it. So first we want to find what the scale factor is. I wonder actually if that's the right way we could do this, if there's might be a better way not to do it that way. Maybe define, I think, as a triangle with that. And actually, is that the same shape as that? So that has to have the same angle as that. If they're parallel, then that should be, yeah, that would be the same as that. Yeah, so I'd actually probably rather do it that way. Considering what we're trying to achieve here, that might be the best way around of doing it. So we'll call this one A, because essentially that is a mini shape of the big one, which will share the same angle of all those angles. We can prove that with parallel lines. And then the B is going to be like the overall. And that's going to get us what we want. So I guess there's a couple of ways that we're going to look at this actually. We need to first of all know what that scale factor is. And then we can start scaling up. Now this little one has a height here of 1.8, and that's the difference. So we need to change that. And this little one to the big one is what we're after. So we're looking for the size that scales up. And we're thinking if we go across like from 1.3 to 1.8, how far have we gone up? It's actually not a very nice number. So scale factor here is 18 over 13. And that's like 1.3. I think sometimes it's easier to see it like that. So it's about 1.3. And that's gone up. And how far away is, I think we're missing that information I didn't write on there. It's 2 meters away, isn't it? So that's 2 meters. And that's kind of useful, I suppose, in a sense. We want to know how much further it goes along. So if it's gone that amount in 2 meters, how many 2 meters have we got like further on? Like it's some sort of scale, isn't it? So we've gone up 1.38. So if that's the conversion in 2, we're going to keep doing that until we get to 30. So yeah, let's think about a formal way of writing this. I guess I'd like it the other way around. Oops. Okay, so I'm looking at a connective information as well here. So if I'm going to scale this up, I know that I'm going to be multiplying by 15. So any length that's going to be on this little one, in terms of its similarity, is similar shape there on B, we're talking something that's 15 times more. Because it's essentially a similar shape. And that would give us a calculation of what we want. And if I'll just highlight this in green from here to here. Of 1.8 times 15, which is 27. So the height of the bandstand. Now that's estimated. So we can do a wobbly equal sign there. But essentially, that's what we're looking at. A little bit confusing, I think, when A, you have to draw your own diagram, but B, you have to decide what shapes are similar. And if I just get rid of this for a second, we can hopefully see that we have parallel lines here and here. And we'll just continue these on. And the parallel lines essentially means, because these two here complement, they're corresponding. And we've got parallel line on the right as well, which this angle is the same. And we know that they've both got right angles in, and we could do the same logic for this one and this one. Essentially, we do have a shape which is similar. It's just been scaled up. So to notice which two shapes are interesting to you, you're going to have to find a link between the two. And ours was the 2 and the 30. because when we redrew this, it wasn't the 1.3 and the 1.8 that were linked up. Those are not two that we can use. Okay, so next, distance AB is 4 centimeters. Find the length marked X. Let's use this color now. I just thought I'd throw in a line there to put people off, but hopefully it didn't put you off. Distance AB is 4. Okay, well, everything's marked. So now all there is left to do is see how we can tackle this. If that's 4 centimeters, be interested to know, like, how much bigger it gets. Now, there you go. That's the link. I don't know if you, I guess it's obscure, but you can see that all of these are the same. So I don't know what it is, but let's call it X. Whatever that distance is, there's 3 of them. And so I think that's the root in that. Oops, what's going on? So you can imagine, for example, that this was, I don't know, 5. Then the whole thing would be 15. So what would the scale factor be? It'd be 3, wouldn't it? Same as if we had each of these were X. So the little triangle, which was 4 and X, versus the big triangle. In fact, that's a bad letter to use, isn't it? Because we've already got it. Call it M. Yeah, so this M, what would it be in the big one? 3M. And so when we're looking for connective information, it's this and this. And even though it's not numbers, we can still see that it's times 3. So we're going to do the same for the 4. Maybe we should write scale factor equals 3. So that's 12 centimeters. There. Okay, so that's similarity for you. Kind of a hidden clue in these lines to show that they're the same. But yeah, you can just like do it in general if you know how much it scales up by. Yeah, I thought this would be a short one. We're already on question 3. An exact model replica of the Statue of Liberty is 40 centimeters tall. Do you know, this is a true story. They made so many when they were originally designing it. And if you ever get to America and you go to see the Statue of Liberty, you can learn about this and see some of these original little models, and some of them very interesting. Used to be a very different flame in the top part, and it used to be like so much metal, like a really Victorian metal thing with real fire candles in. It's much clearer these days. So this one is 40 centimeters. And did you know that, a fun fact, that if you go there you'll find this out, the whole thing was constructed in France as a gift from France, an artist. And it was built in the back garden of the artist. And a lot of people saw it being built bit by bit in France before it was shipped over bit by bit by boat, I believe. So that would have been very fun to see. and then one day disappear. The real statue is 93 meters high. I'm actually not going to draw that again. Let's see if I can scale it up. Okay. Huh. Okay, there's gaps, but it'll do. So it's useful now. What we found is that we have a connection between the two. And the connection is a one-dimensional connection. Height. And height is just measurement in one direction. So it's pretty straightforward to find how something scales up if you only care about one dimension. 93 divided by 40 is 2.325. So currently the scale factor in one dimension is 2.325. And it goes on to say, the real has a volume of 2,500 meters cubed. So volume is 2,500 meters cubed. Now, if you know what 40 centimeters is, you'd probably guess that this doesn't even have 1 meter cubed, right? Because a meter cubed is a meter by a meter by a meter. And if this is only 40 centimeters, it's very unlikely that it's anywhere in even half of a meter cubed. But that gives us perspective here to know what to expect. But the question is, what is the volume of that small one? So huge volume, scaled down. So the first step, I think we need to make this mistake together. Okay, so the first mistake would be to look at the scale factor and divide it by 2.325. Oh wait, hold on. Did I do the scale factor right? No. So I'm getting ahead of myself. There's no way it was 2.325. Should have warning alarm bells. 93 divided by 0.4. Yes. Make sure that this is in the same units. You should always be double checking, and that's why alarm bells go off, like lizard brain goes off. And it did for me there. So that's going to be a scale bigger. Much more like it. It's 232 times. So if we make that mistake together of, turns out this is our second mistake, but hey. Dividing it by 232.5, so 2,500 divided by 232.5. And we kind of get some warning bells, right? 10.7 meters cubed. Because 2,500 divided by this, if we were going to make it 232 times smaller, just like the height got that much smaller, does that same principle apply to volume? No. Because we know it doesn't even take up half 1 meter squared, so how can it be 10.7, which is rather huge? So what's going on? Well, the principle can be seen quite simply. How do I put this? I'm going to do it in 2D. So if I have 1 meter by 1 meter. Is that the best way to do this? Yeah, sure. Maybe we'll do 10. And then we're going to, let's say, scale down to this area, which is 1 by 1. Now let's make it 2 by 2, because then it's more exciting than 1 meters like this. Now we can see very clearly that this will be 4 meters squared. And that this, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 10 by 10, which is 100 meters squared. Now, if we scale this down, 10 divided by 2 is 5, so it should be 5 times smaller. But is it 5 times smaller here? No. If we divide it by 5, we've only got, like it should be 20, but it's actually just 4. And the real reason for this is because when the scale factor operates, it operates in only the sides of the shape, the edges. But because there's one side to convert bigger to 10 and a second side, then it's not just multiplying it by 5. Let's say we're going the other way now. If I'm going up to here, we're not going to multiply it by just 5 because one number got bigger. You're going to multiply the second dimension by 5 as well. So in fact, when we're going across area, it's the scale factor squared because it's 2 dimensions to multiply. And I think you can see it easier in the calculation. So the area of this one here would be 2 times 2. And if you were to multiply both sides by 5 to make that shape scale factor 5, you would get 2 times 5 to make that side bigger, and 2 times 5. And that would give you your 10 times 10. But if we write this in such a way that we see it as 2 times 2, which is the original area, and then the 2 5s, and then you can see that it is the original area multiplied by the scale factor for one dimension squared. And the same thing is true if we're talking about volume. But you probably guessed it. Let's say it was 3 meters cubed. How the volume scales up would have been, if you're keeping the same scale factor, 5 cubed. Because you've got to multiply each dimension. So the 3 is multiplied by 125 and becomes 375 meters cubed, and it gets ridiculous. Scales up very big. So what we're learning is that for every dimension that you're going to be scaling up, you need to be multiplying the scale factor by each dimension. And that works going backwards if you're going to scale down. So we know what the scale factor is here. And essentially that maps the height from here to here. And if we talk about volume, and we went from here to here, it would be times 232.5 cubed. So if we were going to go backwards, we divide it by 232.5 cubed. So as I say, when we do these lessons, we're not necessarily doing just the revision. These live streams are, I guess, for people that have extra questions, but also if you're stuck and you've never get taught it before. So we go through those concepts from the beginning and like why they come about. Let's put this in a calculator now. 232.5 squared. No, not squared, cubed. Equals. That's more like it. 0. Now we'll come in the calculator. Let's talk about this skill as well. It's called standard form. So you put it in the calculator and you're presented with this. And sometimes it looks like e minus 4. Okay, so these are the same thing. But how do you deal with this? Well, this is standard form. And if you want to know, technically that is 1 over 10 to the 4, which is 1 over 10,000. So essentially, this here means divide it by 10,000. So you get 10,000 times smaller. But we can do that a little bit easier if we think about decimal places. It's going to shift and make this smaller by 4. So 1, 2, 3, 4, and there's the new decimal place. Like that. Seems to be a bit of a delay here on the pen today, but let's do that properly and think. If you're going to shift it 4 times, it's going to take 1 to get to there, so you're going to have 3 zeros. One 9. So I was going to maybe go to that. Even that might be a bit too long actually. I will go to, if I'm going to round it to 2 decimal places, maybe I'll go to 1, maybe I'll go to 2 0. Because that 9 is, I know it's awkward, but the 9 is going to go up to a hole if I stop it there. Because of the 8, and then that whole 10 is going to move into the next column, but I have to leave this one because it kind of shows where it was. So if I do it to 1, 2, 3, 4, 5 decimal places, then I have to actually write 5 decimal places. But let's say we round it to this meters cubed. And that's just the way it is. Okay, so there's a whole lesson, and it's a really fascinating relationship between the scale factor and different dimensions as we go up. All right, next one, and last one. We have calculate the length of AD. Diagram not drawn to scale. Well, I bet it isn't. I know it isn't. It was tough to draw it, so I just said not to scale. We're good. Because how can 6 look like that when 10 looks like that? It's just suspicious. So don't take this to say, oh, I'm just looking at it and I think I can see the answer. Definitely not going to work here. Let's go. So calculate the length of AD. Okay. Das dear. That's right there. If that's 6, it means that this is also 6. And this interesting thing with this question, I think it tells us much about like where things are placed or anything. But what kind of triangles do we have here? That's the question. We've got an overall triangle. I'm just going to, oh, wrong way around. I'm going to draw it in here. And the bottom is 16, apparently. And this is 20. And I suppose we could find the other side with Pythagoras, but we'll leave it for now. But I know this is 16 because, let's add those two together. Okay. And then if we draw another triangle inside that triangle, like in here, then that triangle is going to be similar, right? So we can draw that triangle out here, and we know that it's similar, and it's being connected by, let's just write 6 because it's looking messy. It's being connected by the 6 and the 16. This is our connecting information. So always look for that link, because your scale factor is what you need. Okay, so how does it get smaller? 16 divided by 6 is 8 over 3. So we divide it by 8 over 3. And dividing by a fraction is the same as multiplying by its reciprocal, so you could also multiply it by 3 over 8, and that would be the same thing. But essentially that's our scale factor. So we'd have to do the same to this. It's going to get smaller by the same amount. So let's leave that on our calculator. 20 divided by answer is 15 over 2. So 7.5. And that's DA. 7.5. You should probably write it right. Make it clear. Part A. Part B. If length AB, there you are. If length AB is 4.5, there's a freebie, thank you. Then calculate length BC. Okay. This is one of those triangle things again. Sorry, similarity gigs. Let's try green. So essentially on our triangle, this is 4.5. And we want to know part of AC. We already know AB, so if we found AC, because let's just make this clear a second, that this here is point C, and that's A. Using our current setup, we can find AC. So let's just do that. Now when we're going from the small one to the big one, it's not going to be divided by 8 over 3. It's going to be times by 8 over 3. So 4.5 times... Let's put the fraction in brackets just to make sure the calculator doesn't do anything we don't want it to do. Okay, so that's 12 centimeters. So we can see that CA is 12. And we know that we're after BC, which is equal to CA subtract AB. And we just found CA was 12. We were told that AB was 4.5. And so BC is 7.5. A lot of 7.5s going around. Finished. Whoop. So this is the end of similarity, and there are your answers. Hopefully that was all you were hoping for, and you got it correct. Any questions? Nada. So just to finish, this is similarity. It's a topic which comes up a lot more than it used to. In fact, it's part of a broader topic called proportion, and these sort of questions are essential because they make up 40% of the GCSE questions. Skills that you have to incorporate into this exam, 40% of them have to be about using proportion. Similarity is a huge part of it. It's the part where proportion ratio meets geometry. And so that's where some people get put off by seeing it correctly. But we'd already seen today one of the most important skills, which is drawing those two shapes separately. The one might be contained inside the other, but you must draw it separately to get a handle on the connecting information to find a scale factor, and then it's pretty much logical after that. All right, it's been great to see you, and I'll see you in the next one.